Right. Hello. Here's my professional research presentation. Moths are less subjected to light traps than they used to be by Battles et al. This paper was published in the Journal of Insect Conservation, and I interviewed Dr. Avalon Owens, the corresponding author. So on this slide is an image of the US from space, and it's sort of inundated in this yellow light. I'll come back to this yellow light toward the end. So put this in your mind right now. Okay. I'm going to start by quickly introducing the sort of quote villain of this story. It's artificial light at night, or ALAN. It's really any anthropogenic light at night. So your headlights, porch lights, light through your windows, they all count. And it is an environmental pollutant. It's linked to diabetes, cancer, and a whole host of other issues in humans. So here's a picture I took in Busan, South Korea, right? So this was in the middle of the night. But it might as well be midday, right? So imagine what this does to people, but also nocturnal insects. So the authors are motivated to see if Alan interferes with light traps. Light traps have been widely used for over a century, actually, to survey biodiversity in populations of positively phototactic night insects. And it might be a problem if light traps no longer provide an accurate estimate, right? Not only for conservation, but for agriculture as well. So we know that full moons interfere with light trap yields, but no one has actually been able to conclusively show that Allen interferes with light traps. So this is sort of the motivation for this study. The research question was, well, will have light traps become less effective as Allen has grown more prevalent? I'd like to point out that there's a diachronic component to this. Okay, so grown more prevalent over time. So we're going to look at historical data, and that's what makes the study novel. So we have two hypotheses here. First is that light trap yields have grown lower than pheromone trap yields over time. And the idea is that pheromone traps don't depend on vision. So if there are genuine changes in the population, it should be reflected in both types of traps. And if light traps have grown worse as a sampling technique, then it should only be reflected in the light trap yields, right? And the second hypothesis is that the difference in yield between light traps and pheromone traps is smaller where there is less ALAN, so less light pollution. So we're looking at differences across species with different levels of ALAN. Okay. So looking at methods here. So to test these hypotheses, the authors needed both historical data and spatial data. Okay, so it turns out that corn earworm moths, Helicoverpessia, were an ideal organism to look at. So these guys are serious agricultural pests. They eat not only corn, but a whole host of other crops. So tomatoes, soybeans, cruciferous veggies. So these are the destructive. Because they're so destructive, the populations have been monitored for at least a decade on farms in multiple states, Delaware, New Jersey, Minnesota, using paired blacklight traps and pheromone traps. Paired meaning they were deployed together, usually less than a kilometer apart. So we have a pretty rich data set. Okay. 25 years from Delaware, 10 years from New Jersey, 16 years from Minnesota. And we have nice satellite imagery from Google Earth for all these years. And I'll sort of show why that matters in a second. So this is a retrospective analysis, right? They're actually going out and so they're not actually going out and doing experiments. They have the data already, and they're going to analyze and take a look at what they can find. So the first thing they have to do was to fill in the gaps in the data. Because it's not possible to monitor the traps every day during the monitoring period, the data the authors had missing days. So looking at this graph here on the x-axis, that's the months, right? So each dot represents a day in the monitoring season. In the y-axis, that's the number of moths caught. So let's see. So the lavender dots here, these are the dates on which the authors had data. The white dots here, these are dates on which the authors didn't have data. So what they did was they just simply extrapolated backwards. If they had data for a day, and the purple, so these purple dots here, and they didn't have any data for the preceding days. They just went backwards, copied, until they ran into a day that actually had data. All right, and then they calculated the amount of Allen around each farm for each year by drawing a circle around a circle of 1 kilometer radius around each farm and averaging the brightness of the pixels within it. Okay. And then they use statistical models to first to obtain estimates of demographic histories, okay, from two different trap types, the light trap and the pheromone trap, and compare these demographic histories to see how much they differ. And second, to test for direct effects of Allen, right, using Allen as the independent variable and the degree of difference between the trap types as the dependent variable. So how much they differ based on the amount of light present. So here are the results, starting from the least surprising results. Okay, so the first the authors found that blacklight traps consistently underperformed the pheromone traps in the past decade. Okay, so x-axis are the years, the y-axis the current earworm moth population in log scale. So it would actually kind of like go like that in reality. Um, so in all three states, the confidence intervals never overlap. So this is the orange is the pheromone trap and purple is the blacklight trap yields. Okay, so the confidence intervals never overlap, meaning it's exceedingly unlikely that this difference resulted from just a random chance in sampling. Okay, and this difference we see between blacklight traps and pheromone traps is not simply due to an innate difference in sampling performance, right, between pheromone traps and blacklight traps. Here's the historical piece that the authors are looking for. Looking at the full 25 years of data in Delaware, we see that up until about 2009, 2010, over here, blacklight traps perform comparably to pheromone traps, right? But something happened around here that caused blacklight trap yields to massively decline until stabilizing in the last few years. Okay. Finally, this is the most surprising and sort of disappointing for the authors, is that they found no consistent relationship between Allen and light trap performance. Okay, so in Delaware, in this line green, um, increasing Allen, so okay, so x-axis, that's the amount of Allen, right? Absolute environmental light level. On the y-axis, that's the sort of the degree of light trap underperformance. So higher means worse performance by black light traps. So in Delaware and lime green, the authors found that the predictions were supported, right? Farms with less environmental light, less Allen, had lower underperformance by the light traps. But the opposite was true in New Jersey in this darker green. Uh, this is perplexing. And Minnesota only had one farm, so they couldn't compare across farms. So they only had one spot here. Okay. So what does this all mean? First, we know that light traps have become less effective at sampling insects over time now, right? So if you're a farmer and you're using black light traps only, you might end up missing the action threshold for a pest moth, right? And if you're a conservationist, you might end up sort of misallocating your limited resources toward a species that might be better off than you actually estimate. So it's important to have an accurate estimate for these things. Second, what happened in Delaware that caused this just dramatic decline in light trap performance in 2009, 2010, right? Over here. So it turns out that from 2010 to 2014, Delaware started switching out their older, longer wavelength streetlights, like the ones you see over here. It's actually from New Zealand, but the point stands. With these sort of ultra bright, short wavelength LED lights. These are more energy efficient, right? But insects see blue light better than red light. So the authors think that when the switch happened, these bright LED streetlights started to compete with the black light traps much better than this sort of older style yellow light street lamps. And that accounts for the divergence. Okay. Finally, the authors failed to show a relationship between light pollution and light trap catches. It's not exactly that there was no relationship at all. It's just that there were different relationships in different states with different kinds of streetlights, right? Moreover, it turns out that blue light can't travel as far as red light. So from space, it's hard to perceive blue light. So even the areas with a lot of blue light can appear darker, even if these areas are actually much brighter on Earth. Okay. So if you recall from the title slide, we had an image of the US from space. It had all this yellow light, right? So it's because blue light just isn't detected as well in space. So using satellite images to measure Allen was probably flawed. Dr. Owens told me that underground light measurements are necessary. Okay, so I'm gonna finish out by covering some of the interview highlights. I chose this paper because I have some previous experience volunteering for a PhD student who was studying moth biodiversity in Boston. Um, so it was a natural extension of my interests. I think the most salient thing I learned from this interview was that science is highly social. This paper had 9 co-authors, and that's not even that many compared to other papers. So I asked Dr. Owens, how did you get so many people on board with this? So she just started talking to people at a conference. She was in person and she started talking, and people who were interested, showed up and started talking with her. So I think it's important to stay social. The most impactful thing for me was Dr. Owens' sort of sense of urgency about this. She said Alan is only ever getting worse, right? And it's always conservation and the difficulty of sustainable agriculture as well. So it's really important to have a good sampling technique to monitor the populations of insects. And so, we probably need an alternative or gotta figure out some way to mitigate this decline in light trap efficacy. Um, all right. And the surprise is Dr. Owens told me when I started graduate school to visit my field site at night, because a whole different set of insects will emerge compared to daytime, and you get this full picture of the site, and so the whole breadth of biodiversity there. It hadn't occurred to me that like such a drastic like sort of a deal difference would exist. So like that kind of surprised me in a good way. And finally, looking back, I wish I asked Dr. Owens, if she received any pushback or faced any challenges in publishing a negative result, right? The authors did show that light traps become less effective over time, but failed to show that Allen is correlated with light trap underperformance, right? It's sort of a little disappointing and a little unsexy, but it's important to have negative results, right? For this, you can't always be getting, positive results, right? So I wish I could have gotten some perspective about sort of publishing this kind of result. So this concludes my presentation. I appreciated taking this course. I felt like I was challenged and pushed to do my best, and I certainly learned a lot from this course and the lab. So thank you very much.